So let's get another problem done. All right, so this is homework 21, and this is problem 1. We have this doohickey here. Rube Goldberg massive mousetrap. It is very massive because it's 2 meters long. Wow, that's crazy. It's more like a garage door than a mousetrap. But anyway, we're going to kill a big rat. So 12 kilograms is this rod, and this is in the vertical plane, by the way. And it's 2 meters long, and the spring is has a spring stiffness of 40 newtons per meter, and its unstretched length is 2 meters. So that's not in the position shown. It's not 2 meters. And in the vertical plane, with the attachment points are 2 meters apart, and the rod is released when theta is equal to 30. We want to find the angular velocity when theta is equal to 90, and find the angular velocity when the spring is unstretched. Well, alrighty then. And yeah, okay. So there's some geometry kind of involved. Let's see things that I want to try to get. Let's do some of that geometry and figure out what the other angles are. I think I was supposed to have this as theta. So, and that's going to be 30 degrees right here at state 1, and that's not really drawn to scale there, I guess, huh? Well, all right. So anyway, if it was 30 degrees, that would be this right here and that right there. And so I want to find what LAB actually is, right? So right here, if this is 30 degrees, then this should be 150 degrees, right? And these lengths are 2 meters each. So we could actually find the other angles right there, right? They should both be, they should both be like 15 degrees. Is that right? Because, yeah, I think so. So does that have to be equal to each other? Sure. And that has to be 180, so that 150, so all these angles add up to 180, so these must be 15 degrees each. And so if I want to find this angle, I could do law of sines, probably the easiest thing to do here. I started thinking I had to do law of cosines, but I don't have to. So law of sines, we're going to have LAB divided by the sine of 150 is going to be equal to 2 meters divided by the sine of 15. So LAB should be equal to, let's see, 2 and 15 sine of that divided, and then 150 sine times it, and we get to this is going to be 3.864 meters. Therefore, del 1, I don't know why I just put another mark there, is going to be equal to 3.864 minus 2, and I could do this in my head, 1.864 meters stretched in the beginning. We also need to know the height or this location right here. That's not too hard, right? Because that's just going to be the 1 meter times the sine of 30, right? No, 2 meters times the sine of 30, but I think that'll be actually 1. So we should be okay. All right, I think. Let me think about that, right? No, 1 times this, it's just 0.5. Yeah, okay, so yeah, because this is 1. Why is that making it? Why is that so hard for me? Right there. Okay, yeah, no, that's 0.5. Okay, good. All right. So anyway, yeah, we have to decide on what the. Let's just start. Sorry, KE1 plus PE1 is equal to plus U1 to 2 is equal to KE2 plus PE2. All right, so there's a work energy problem we're doing here. And my head's just not in the game right now. Oh well. KE1, we're going to start from rest. All right, so KE1 is equal to 0. The PE1, this is something, I kind of want to draw another figure for this. So now I'm trying to think of where I want to try to do this. So let me draw it over to the side, right over here. All right, so I'm going to draw basically the same thing here. But we're going to do it for purposes of trying to set what the datums and that kind of thing are. Right, so here's the length of this piece. So the datum should be right there, right? And that should be state 2, and this is state 1 right here. And so we can have, that could be the datum. So we want to, so this is the center of this thing. We also need to have the center right here. So we want to try to figure out what this length is going to be right there, that height change, so that we could do the potential energy at state 1 right here. And I'll call that delta Y 1 to 2. Right. So I'm also thinking about part B in this. We're going to have to figure out the angles for part B. Right. So that's coming up. We might have to do a reset in our numbering and our datum. But for now, for this one, between these two positions. So this height right here, right? So this height right here is going to be 1, right? This distance, because this piece is 2 meters long, right? And so this distance right here would be this 1 right here times the sine of that angle, which is 30 degrees. So that's 0.5, right? So that would be the distance here. So this right here is actually 0.5. So we find that our delta Y 1 to 2 is equal to 0.5 meters. So let's see. KE1 equal to 0. PE1 is going to be equal to mg time delta Y 1 to 2 plus 1/2 K del 1 squared. All right, so let's get all that in there. That's 12 kilograms times 9.81 times 0.5 plus 1/2 40 times 1.864 squared. That E is terrible. I'm going to fix that. E. So we have 12, 9.81 times, and then 0.5 times. So this portion right here, that comes out to 58.86. And so this other guy, 1.864 times 40 divided by 2, that ends up being, does that look like, yeah, 69.49. So added together, they are 128.4, and these are Newton meters. And there is no losses or anything external going on here. We haven't applied anything, so there's no work there. And oh, some more geometry that I need to do. I need to figure out the spring length when it's right here, right? So that shouldn't be too hard. That should be, the spring should be at 45 degrees because this right here is 2 meters, and that right there is 2 meters. So we could say that looking for LAB1, let's say LAB2 is going to be, well, it's really just the square root of 2 squared plus 2 squared, right? I think that's the easiest way to do it. So square root of 8, right, should be 2.828 meters, right? So del 2 in this case is 2.828 minus 2. I'm getting a phone call. Let's see who that's from. State of Connecticut. Let's see. I will answer these guys maybe. Hello?
Hi, my name is Sarah, Senior Health Advisors Insurance. How are you today?
I can't believe that I just answered that call. I thought I just paused the video for this. Oh, never mind. Another insurance thing, another scam. Hate these people. All right, so we get 0.828. It said State of Connecticut something or other on the phone. So I don't know. It could be the state cops or something. You know, it could be my kid in a wreck or something. I can't stand. I hate these people. Wish they just. Wish you could do something back to them. They could make them charge them more money for making that phone call. All right. So anyway, KE1. Oh, we need to be able, before we do this, I need to do some preliminary stuff I forgot to do. Normally I need to get the mass moment of inertia of this piece, and because it's pinned, it's going to be a little bit easier to find the mass moment of inertia about A, right? So we will find the mass moment of inertia about A by finding I bar of the thing, right? And plus the mass times the distance squared that we're going to move it. So this thing is 1/12 MAC times LAC squared plus MAC times LAC over 2 squared. Truth is, you know, a lot of times we can actually look. There's actually a lot of times that for a beam they'll actually have what the mass moment inertia is about the end, so you can simplify that. But anyway, I didn't manage my paper very well here. But what the hell? 12, and the length is 2 squared plus, let's see, you're going to have 12, and then we're going to have the length is 2 over 2 squared. So first off, we get, oh, look at that. We could do that math ourselves, right? That's just going to be 4 and then plus 12, right? 4 plus 12. 16 kilogram meter squared. And that was easy. Should have we should use that in these values on a test, right? Make it just fast, right? That you can go 12 divided by 12, and okay, cool. So anyway, that's going to make it easier here. We go 1/2 IA omega 2 squared, right? Or just 1/2 1600 omega 2 squared. All right, and then PE, and I just wrote KE1. Why the hell did you do that? KE, okay. And then PE2, right? So the gravity is at its datum at state 2, but the spring still has a deformation. And so we get 1/2 40, and we just wrote out the deformation over here of 0.8284 squared. So that ends up equaling 160. That doesn't make sense. Why is that more than that? Okay, so I did something wrong. Oh, I know. I didn't take out that 2. That's why. Okay. 0.8284 squared 40 times 2 divided. Okay, that's what I did wrong. So, whoa, 0.8284. I don't know what the hell I just did. 40 times 2 divided. Okay, so that should be 13. That's, yeah, it makes sense. 13.73 Newton meters. And we've run out of paper, so let's go to the next page. We have 2. This is problem 1, continued, ... So, let me see here. We're filling out this equation right here. We're entering all the parameters in that equation. So, we get 0 plus 128.4 plus 0 equals, all right, so this would end up being 8 omega 2 squared plus 13.73. And so omega 2 is equal to, let's see, I subtract out my 128.4, divide by 8, take square root. And so I say I get 3.786 radians per second. And now we have to do the third, or part, this is part A. Part B is now going to find, well, let's draw the thing out here. All right, so here's going to be 2 meters, but now here's 2 meters, and then 2 meters, right? So we're going to need to find this. These are all 60 degrees right here, right? But then it started out over here, and I'll kind of like make it over like there. Here was the 30 degrees, right? Not really looking like it, I guess. I guess so. Yeah, that seems about right. Okay. Which had a height right here. We could measure it off of this, was equal to 0.5 right there, right? But now we want to find what this height is going to be right here, and they almost look like they're the same, and they shouldn't be. All right, so let me try to make it look a little bit better. Right in there, so it's a little bit down like that. All right. So that right there should be 0.5, and I'm going to exaggerate this up just a little bit right there, so we can see that it's in the center. So now this time, sorry about that. All right, here is going to be delta y from 1 to 3, right? Because this is going to be state 3. This was still state 1. Come on, focus. Gotcha. Okay. And all right, so delta y 1 to 3. All right, so here, so this is the new, we'll write this as datum, or reset the datum right there. And delta y 1, 3, this is going to be 1 times the sine of 60, right? So I'll write it out. 1 times the sine of 60 minus 1 times the sine of 30. And it's supposed to be equal sign. 60 sine and 30 sine and minus, and we get 0.3660 meters, right? So now we're going to do much of the same thing. Well, let's just write it out. K1 plus PE1 plus U 1 to 3 is equal to KE3 plus PE3, right? So now PE3 is going to be 0 because the string is unstretched, and that's going to be the datum. KE1 was already equal to 0. PE1 is now going to be mg delta y 1 to 3 plus my 1/2 k del 1 squared, which remained the same thing right there, right? So we got 12 kilograms, 9.81, this 0.3660, and then plus 1/2 40, and then 1.864 squared. So we're going to end up with, let's get 12 times that, 9.81 times. All right, this part ends up to be 43.089, and then this is 1.864 squared, 40 times 2 divided. That was that 69 that we had before, so we add them together. So now the potential energy in the beginning is actually 112.6 Newton meters. And the KE3 is still 1/2 I about A omega 3 squared, which was 1/2 16 omega 3 squared, aka 8. I guess I'll put all the sig figs in there, and I kind of feel like it's silly. That's all right. And then PE3 should be equal to 0. So all we get here is 0 plus 112.6 plus 0. I didn't bother writing out. I guess I should have written. There's nothing happens in between these two. It's going to be equal to 8. Here's your sig figs. Omega 3 squared plus 0. And so omega 3 becomes 3.751. So it's not. It didn't actually even change all that much, huh? All right, because the other one was 3.786. That's interesting. Okay. Well, let's. You know, that I could do this in a computer simulation. It would be kind of interesting to do, but I can't do it right now because the video card on my computer, for some reason, doesn't let me do remote stuff on my work computer in my office. So I can't remote to it. I guess I could remote into the one of the lab computers, and might as well make this a vector. And we're saying it's going clockwise, so so omega 3 is 3.75 radians per second. There you go. All right. Another one down the hatch here. 24 minutes.